Thank you very much. Pleasure to be here, and I thank Gilles in particular for the invitation. It's a great place to be. So I'd like to talk about multinorms and something that's been a strand of what I've been thinking of for the last 4 or 5 years. I've got a collection of references here that you won't take in too quickly, but there are a list of papers here, and if anyone would like to access any of them, I'd be happy to supply them. Of these, the one called DP was an original paper in this area published in Decompositions, and the second one there is a survey article on this that appeared as a consequence of a meeting in Tartu. And I'll also in particular refer to D-Lot near the bottom, which is a paper with Niels Laustsen of Lancaster and Timur Oikhberg, whom I've never met, in Illinois, and Vladimir Troitsky of Edmonton, and this is almost complete. So let me start with some definitions. We are always based on a norm space, which is really always going to be a Banach space. And e to the n is the n-fold Cartesian product of this space. And we put a norm on the nth Cartesian product. So we get a collection of axioms A1 to A3 that tell us what this sequence of norms does. And the first one just says that if you look at an n-tuple and you permute the variables, you don't change the norm, which is an innocuous axiom, I think. The second one says that if you multiply by the individual vectors by complex numbers of modulus at most 1, you don't increase the norm. And the third one says we've got to have a connection, of course, between the nth and the n plus first norm. And the axiom A3 says that if we put a 0 on at the end of a vector and make it into an n plus 1 vector, and measure that in the n plus first norm, we get the same answer as we did when we did it in the nth norm. Of course, there's no significance in where we put the 0 because of axiom A1. So the original concept that we had was a somewhat less obvious axiom, and this gives us what we call a multinorm, and this says that if you add on to your n-tuple another vector that happens to be equal to the last vector, thus getting an n plus 1 tuple, we don't change the norm when we multiply, when we calculate the norm in the n plus first stage. And it's perhaps not quite obvious why that's a reasonable axiom to start with. There's another way of doing this, and that came up, and this time we have an axiom called B4. The numbering is not ideal now, but it's what we started with. And then this says that if you add an extra vector at the end that's equal to the last vector, but this time we put the number 2 in front of the vector x to the n. So we have what I call, in what's probably unfortunate notation, a multinorm and a dual multinorm. A dual multinorm is not necessarily defined on a dual space. It's just defined on a Banach space. Now, of course, there is a way of putting dual norms on it. And I realize from looking at what is said here, my notation is not normal in the Banach space community. For me, a prime denotes the dual of a Banach space. This is from my childhood, how I did it, and too old to change now. So throughout, a prime for me means a dual space, and a prime on a norm means the norm on the dual space. And it's sort of obvious that the dual of the n-fold product is the n-fold product of the duals in an obvious way. So we have these ideas of a multinorm and a dual multinorm, and each is the dual of the other in a certain sense. And if we have a multinorm with a starting space being the normed or Banach space E, we say that we're based on the space E. And I thought I'd try to make a little propaganda about why we can have any value in multinorms. The proximate cause of introducing multinorms was something I'm not going to talk about at all, but it came from an explicit question in the theory of Banach algebras, which I'll just describe in a couple of sentences. If you take a locally compact group, we put the group algebra L1 on it, then we have the concept of bimodules and left bimodules over this. An obvious left bimodule is LP of G, so this is a left bimodule over the group algebra L1 of G, and it became a question of interest within Banach algebra theory whether or not LP of G, in the case where P is strictly between 1 and infinity, this is not true at 1 and in infinity, whether it became what's called an injective Banach L1G module. And there's a theorem of 30-odd years ago of Barry Johnson that said that if the group that we start with is an amenable group, then it is indeed an injective Banach L1G left module. And Barry asked me, or and others, 30-odd years ago, whether the converse is true. And so with Maxim Polyakov, who came to Britain on a UK-Russian exchange, we attacked that question, and eventually, after some time, we did indeed prove that the converse is true. So the converse of that theorem about group algebras says that LP of G is independent of P within the reflexive range, is an injective L1G module if and only if the group is abelian. And our formulation of this question, amenable, yes. Our formulation of this was in a language of multinorms. We didn't think of the abstract theory of multinorms and then find a question to do it. It was an abstraction of the solution to a question. But then once we'd got a tool that could be used to solve at least one problem, we thought, well, maybe we look around for a few more problems that it could solve as well. So I claim that that multinorms are good for understanding the geometry of Banach spaces. You'll see in a few moments a strong connection with the theory of absolutely summing operators. And then we'll find that the morphisms in the category we'll call multi-bounded operators, and they will, I think, prove to be some interest. We can apply the results to Banach lattices, a subject about which I know very little, and I'm hoping that there are experts here who could tell me one or two things about Banach lattices as we go along. And but I think it gives some insight. And I'll also mention a theory of decompositions, which is particularly related to the work of Nigel Kalton. Okay, so let's suppose we've got a power norm. Well, it's an easy calculation to show that the nth norm of an n-tuple is at least bigger than or equal to the maximum of the norms of the xi, and less than or equal to the L1 sum of them, so that on any particular level n, all multinorms are equivalent. The point is there's a constant that depends on n coming in this, and the whole game is concerned with the behavior of this constant as n tends to infinity. So we could, of course, take the left-hand side of the equation that you see up there and define that to be the nth multinorm, and you just check that that is a multinorm, and it's the minimum one, where minimum is defined pointwise in a sense. And if you look at the equation star there, it follows that there is a maximum multinorm, but it's not the right-hand side of the equation because that is not a multinorm, it's a dual multinorm. What is the maximum? We'll come to that in a few moments. Okay. Then, as we look at it, we can see there's a characterization of multinorms. So for this, I've got to look at the space of matrices, and I put norms on the space of matrices corresponding, well, on the first line there, it corresponds to the map from the L infinity norms on Ln and Lm. And so, and a matrix, of course, acts on the nth power of a Banach space in an obvious way. So let's suppose we've got a sequence of norms defined on the successive Cartesian powers of e to the n that start at the right point. And I want to know whether this is a multinorm or not. Well, the theorem is that it's characterized by the equation in the theorem, that if we take a vector in the n at the level n, we take the norm of the matrix regarded as an operator, and we find out the image is in the m-dimensional space. We just need the norm to satisfy that inequality. And that's a characterization of multinorms. And in fact, well, it says you've got to check it for all matrices at that level, but in fact a rather small subclass of matrices will survive, will be sufficient for checking that. Once we've got this, you can see there's going to be an obvious generalization of a multinorm. So in this case, I then put the LP norm on the finite dimensional spaces and then look at the matrices. And I now have a P multinorm, which is that which satisfies the equation that we have in the definition there. So if you're keeping track of this, what is now called an infinity multinorm is a multinorm in the old sense, and what is now called a one multinorm is a dual multinorm in the old sense, and I'll use this terminology from now on. You can see rather quickly that if we've got a P multinorm, it is a power norm in the sense that it satisfies axioms A1 through A3. And it's a little exercise to show that if you start with a P multinorm based on a space E, and P prime is the conjugate index to P, then when we take the dual, we finish up with a P prime multinorm based on the dual space. Well, I'm sure everybody knows this, but let me just remind you what I call the weak summing norm here, and at least I introduced my notation. If we've got a norm space and we've got an index P, and we've got vectors x1 to xn in our space, we look at the sum that is very familiar. We take this, I use the angular brackets for the action of a linear functional lambda on the vector xj, and we take the supremum on the right-hand side, where of course we're taking the supremum through the unit ball, closed unit ball of the dual, and we have what is called the weak P summing norm. And there's a little formulae for the weak one summing norm underneath there. Well, it's easy to check that this is a P multinorm in the sense that I had before. Now, if we start with, well, we've really got a dual of this, and this is what I will call new Pn. I mean, we take a dual, we go to the second dual, and then restrict it back down again. And so we get not only mu Pn, but we get its dual new Pn, and therefore we've got two of them in symmetry, and these indeed are P summing norms. And the next example, which I see I've called example 1, but is of course example 2. And this is, we try just defining a very obvious norm here. We take the norm of an entupole to be the sum of the pth powers of the norm with 1 over p coming in at the end, and call this the p sum power norm. And then of course one would like to know whether this is a p multinorm or not. And it turns out that the following are equivalent. First of all, that it is a P multinorm. Secondly, that E is a P space in the sense of Hertz, and that really almost means, by the definition, tells us that. And it's also is equivalent to E belonging to the class SQP, which I'm lifting notation from the that I see in the literature, but I'm sure there are people here who know this much better than I do. So this is the class of spaces that are closed subspaces of a quotient of an LP space, or equivalently a quotient of a closed subspace in an LP space. And the connection of this goes back to a theorem of Quapian, and I think is well known to Christian Lemurdy, and who has generalizations of this result. Okay. Now, when we're looking at the certain representation theorems that are going to come up in a few moments, it turns out that we need a strengthening of the concept of a p-multinorm, which we call a strong p-multinorm, which I'll explain now. So in this case, let's take vectors n-tuples x and m-tuples y and hit them with a continuous linear functional lambda. And we have an expression that's given in the equation up there. So I say that y is less than or equal to x with respect to p if we have the inequality that's on the slide up there. And a strong p-multinorm is something that is a sequence of norms on the nth powers of e with the property that whenever y is less than or equal to x, there's corresponding norms of the n-tuples and the m-tuples, and I said my m and n the wrong way round. This is an endemic problem in this game, to keep m and n the right way round. That's something that's called a strong p-multinorm, and it's a little exercise to check that if we've got something that's called, that I'm calling here, a strong p-multinorm, it actually is a p-multinorm. This implies that it satisfies the earlier conditions. And the position, in all these concepts, you can try to decide whether it passes to subspaces and to quotient spaces, and when you take the dual space with an appropriate change of the index, it passes to dual spaces. I think I forgot to say that the concept of p-multinorm does pass to subspaces, quotients, and duals. The concept of a strong p-multinorm passes to subspaces, but not necessarily to quotients or duals. And then we have a theorem that says, so this is a strengthening of the concept of a p-multinorm, and we'd like to know whether it really is a strengthening or whether perhaps every p-multinorm is already strong. And the answer is if p is 2 or p is equal to infinity, that is correct. Every p-multinorm is a strong p-multinorm. But that was the easy bit. The less easy bit is to get counterexamples for other values of p. So now let us take p that's not equal to 2 and infinity and look at the p sum power norm that I had a couple of slides back. We know when this is a p-multinorm. It's when we're in the class SQP. But that particular example is a strong p-multinorm if and only if you have the stronger property, not of being isomorphic to a quotient of a subspace of an LP space, but actually to be isomorphic to a subspace of an LP space. So in this particular setting, there's a difference between the two conditions. Then we have to find specific examples of spaces with this property. Well, if p is bigger than 2 and less than infinity, we just take an appropriate value of the space little lr, and I pay a tribute to the book of Albiach and Kalton, because of course we just find this example by looking through the pages of Albiach and Kalton. On the other hand, we had some trouble finding a counterexample when p is between 1 and 2, and this conference had great value to us because we saw the name of Professor Schechtman in the list of people who were speaking here, and I looked up the example that he was referring to in his abstract. This is one of the first times in my life that I've actually used an abstract to get a theorem, and if I've got this correct, his space ZP that came up in a talk. Should I have a bar on the... Okay, maybe you can check my calculation to make sure I've got this entirely correct. But I claim that if we take p greater than or equal to 1 and less than 2, and look at your space ZP, and thank you for that remark, then I believe that's isomorphic to a space in the class SQP, but it's not isomorphic to a subspace of LP. Do you think that's correct? So he nods, so that reassures me that I'm understanding his example more or less correctly. Okay. Then there's another example. So remember the question I was addressing is whether every p multinorm is already strong. I know this for p equals 2 and infinity. I want a counterexample for every other value of p. Well, if we start with the obvious weak p summing norm, it's easy to see that this is a strong p multinorm. But its dual is what I call nu instead of mu, and that's always a p multinorm, but it's not always a strong p multinorm. And by doing some calculations, you can find that for all the bad values of p, you can get a finite dimensional space F, that when you put the weak p summing norm on that space and then take the dual on the new pn on the dual space, you get a p multinorm that's not strong, and that involves some calculation involving projection constants and so on. You might wonder why I'm going on at some length about the difference between p multinorms and strong p multinorms, but this I hope will become clear in a minute or two. Well, you probably recognized something that I was a little slow in understanding, but I think I've got there now. And this is that I'm really doing the theory of tensor products here. And so let's see how we can translate all this into the language of tensor products. So we have now, we take a suitable value of p, and we look at the tensor product of, just the algebraic tensor product of the LP space with our normed space E. And for me, delta sub j is just the sequence that's 1 in the jth place and 0 elsewhere. So we could put a norm on this tensor product. And the condition that we put on for this norm is that if we have a compact operator on little lp, then we can calculate the norm of T tensor, the identity on E, with respect to the norm we've put on the tensor product. And I want this to be equal to the norm of T. In this statement and for the rest of the talk, to get the correct result for L infinity, you have to replace, for P equals infinity, you have to replace L infinity by C naught. Well, as you'll guess, the p multinorms defined on the tensor product correspond exactly to p multinorms. And the formula I'll give in a moment. If we take the injective tensor product and LP tensor E, we get the weak p summing norm, which is exactly the minimum p multinorm. And if we take the projective tensor product, we get the maximum p multinorm, which is, of course, exactly nu of Pn in this setting. And the recipe is that if you have an interpol, you look at the tensor delta j, tensor xj, you add those up, you look at the norm of that in the space, and that takes you over to the multinorms. So this, in fact, is recapitulating stuff that I think Pisier and probably many people perhaps in this room and in France were well acquainted with long before I discovered this. Let us now apply this in the particular situation where we start with a Banach lattice rather than with a Banach space. And for me, throughout, a Banach lattice means a complex Banach lattice. And that is actually important because some of the results I'm going to state are not actually true for real Banach lattices. So I take an n-tuple in a Banach lattice. I take the moduli of those, each of the n-tuple elements. I take the supremum, and that gives me the norm superscript L, the lattice multinorm, based on that. And it is a multinorm, or an infinity multinorm in the new terminology. And then I could take its dual, in which I take the sum of the moduli instead of the suprema of the moduli, and that gives me what I call superscript DL, and this is going to give me a dual multinorm, or what is now called a one multinorm. And these are the Banach lattice multinorm and the dual Banach lattice multinorm. And each is the dual of the other in the sense that if you start with one of them on a Banach lattice and take the dual Banach lattice, then the dual norm corresponds to the other one. And this obviously again suggests a definition, a generalization. So now we're still in a Banach lattice. We take the element that is the modulus of xi to the power p, add them up and take the pth root, which is of course defined by the Krivine calculus, and we get what's called a p multinorm, and it's the canonical lattice p multinorm for us now. And by taking p equal to 1 and infinity, we get back to the previous concepts. And this is not just a p multinorm, it's a strong p multinorm. We also observe that when you pass to sublattices, and if you pass to appropriate quotients of lattices, the relative quotient p multinorm is indeed the canonical lattice p multinorm on the quotient. But that turned out, as far as we can see, to be a non-trivial theorem. It took us a certain amount of time. That's not just entirely obvious. That took a fair amount of calculation to do that. So we've got various examples of multinorms. There are many other examples, one or two of which I'll mention later on. But now I want to turn to the concept of multi-bounded operators. And I think the first bit is very well known. Well, let's start with Banach spaces E and F, and then look at a map from e to the n, the nth power of e, to the nth power of f. And of course, there's an obvious amplification of the map T to this space. And if we've got norms on e to the n and f to the n, we can look at the norm of the nth amplification. It's called, it's written in the formula there. And of course, for each n, that's a finite number, but the question is, what happens to that number as n tends to infinity? And this gives us the multi-bounded norm. Of course, those who know the theory of operator spaces will see a strong connection with the theory of operator spaces. And in particular, in the case where p equals 2, this is a theory that's been well developed in the theory of operator sequence spaces. But we don't care to concentrate on the case where p equals 2. There's an obvious concept of a multi-isometry, a multi-contraction, and so on. And there's going to be a notation of this. Right. Well, now I'd like to mention a representation theorem, which we sort of proved ourselves, but we've then found that is known in the literature. The first, a special case of the theorem that I'm going to mention appears in a thesis of someone called Marcolini Nahani, and the theorem he attributes to Pisier, and it was indeed Nigel who pointed out this reference to us. Later on, we discovered that a proof of Pisier's theorem was given in a paper of Peter Kazaza and N.J. Nielsen. I think there's another Nielsen here who is not apparently the same person as this one. And then, and this comes from Bill Johnson, we discovered very late in the day that a thesis of a student of Bill Johnson in a very different language and different proofs has a theorem that's rather close, or perhaps the same as ours. So what are the representation theorems we've got? What we'd like to know is that if we start with a p-multi-norm on an arbitrary Banach space, it's given in a canonical way in connection with lattices. So looking at the theorem near the bottom of that, it comes this way. Let's start with a p-multi-norm based on a Banach space. Banach space E, what we'd like to do is to find a Banach lattice and base the canonical p-multi-norm on that. But, well, that's not going to work. We do have to drop to a closed subspace Y of our Banach lattice X, not a sublattice, but a subspace. And then we'll have a canonical p-multi-norm based on the subspace. So that gives us a chance of being a general result. And then we'd like to map our arbitrary p-multinorm onto the canonical lattice multinorm based on the sublattice Y. And can we do that? Well, we better have a start with a strong p-multinorm, because the answer's a strong p-multinorm and it wouldn't work otherwise. And we also have to bring in the definition of p-convexity, which I won't explain, but is obvious, and these conditions are equivalent. So the theorem there is a general one for p-multinorms that's in our latest preprint. This is quite a long theorem. The particular versions for 1 and infinity multinorms are cleaner and clearer, and they're stated at the top. So this is the summary of our representation theorems. For the next bit, I need to know a little bit more about Banach lattices and maps between them. So I'll just quickly summarize some well-known facts about maps between Banach lattices. We all know what a positive map between Banach lattices is, what a regular map is. It's just a linear combination of positive maps. And we use the term a pre-regular operator for an operator whose dual operator is regular. I don't know whether that's a standard notation. Maybe someone can tell me. On the regular operators, we put the regular operator norm. And so we get a Banach space with respect to the regular norm. If the spaces are equal, we get a Banach algebra. And this interests me because it seems to me quite an important Banach algebra, and it's barely studied. For example, in the book I wrote on Banach algebras, it's not mentioned. Okay. We also have the concept of order-bounded operators between Banach lattices, and this is summarized very quickly on this slide. I think everybody will know this, and it's a well-known fact that, looking at the equation at the bottom, that every regular operator is order-bounded. Every order-bounded operator is pre-regular. And all these inclusions can be proper, although on fairly modest conditions on E and F, we get quite a lot of equalities there. And so what I have in terms of maps between Banach lattices, we can reinterpret this in terms of multi-bounded operators. So we take two Banach lattices, E and F, and we put the canonical P lattice multinorm on them. Therefore, we have the concept of a P multi-bounded operator between two Banach lattices. So how does this relate to the previously known concepts? Well, if P is equal to infinity or 1, we get back to exactly the pre-regular operators, not the regular operators. We get back to the pre-regular operators. If P is equal to 2, we get all operators, and this uses a deep theorem of Krivine, and you probably know that in that equality there, Grothendieck's constant is going to come in somewhere. And then let's say, look at the case when P1 lies between, P1 and P2 lie between 1 and 2. Well, we increase with P. If we start at the bottom, when P is equal to 1, we get the pre-regular operators. By the time P has got up to 2, we get all bounded operators, and I don't know the characterization of exactly what we get in the in-between. Well, this has an application to the theory of decomposition of operators that I'd like to explain next. And first of all, there's a standard concept in Banach space theory of a Hermitian decomposition of a Banach space. So if we have a Banach space E, we write it as the closed linear span, closed decomposition of subspaces E1 to EK, a direct sum decomposition. Decomposition is said to be Hermitian if whenever you multiply all the components by a complex number of modulus less than or equal to 1 and add them up, you don't increase the norm. And the reason for the terminology Hermitian decomposition is that it just says that the projections onto the components are Hermitian operators in the sense of numerical range theory. And it's a little observation that if we pass the duals, we preserve Hermitian decompositions. We can also have the notion of decompositions with respect to multinorms. So let's just look at this for a moment. If we've got a multinorm space and we've got a decomposition, I'm saying that the decomposition is small if whenever you take an n-tuple and then you project that the components of that down onto their respective spaces and work out the norm in the space of those projections, it's not bigger than the multinorm that we started with. Another concept is that of orthogonal. And this says that if you take a k-tuple and the individual vectors belong to the specific k spaces, then you just add up the norms. We don't have to take the projections now. We get exactly the same norm. And it's an easy theorem that a small decomposition with respect to a multinorm is an orthogonal decomposition, and this is certainly a Hermitian decomposition. The converse of Hermitian does not imply orthogonal. It's an aggravating question that I've spent a few evenings on, trying to work out whether small and orthogonal is the same. And earlier in this conference, I saw some beautiful diagrams of polytopes. And I'm trying to interest somebody in this because I believe there's a counterexample to this, and it's got to be in two-dimensional space, which is the space C2, which is four-dimensional real space. And you've got to draw a polytope in four-dimensional space. And I thought there are people here who might be very good at that, but it was too hard for me. Okay, then we could have a theory of decompositions with respect to Banach lattices. So when I'm talking about decompositions with respect to Banach lattices, I'm talking always about the lattice multinorm based on the Banach lattice, which formula I've recalled just there. In a Banach lattice, of course, we have the well-known notion of a band decomposition of a Banach lattice. And it's easy, almost a triviality, to see that a band decomposition of a Banach lattice is small in the sense that I defined on the last slide, hence orthogonal, and that's clear enough. But I couldn't do the converse. And that's where Nigel Kalton comes into this story. My formulation of the question was the converse of the last theorem true? And you can reformulate this entirely as a question about Banach lattices. You don't have to know any of the theory of multinorms to get the reformulation. So the reformulation is just what I've got at the top of the page there. We have a decomposition that satisfies the equation at the top, and I need to show that forces the decomposition to be a band decomposition. That's exactly the converse of the theorem that I had. Well, I thought, oh, goodness me, anybody in the Banach lattice community will surely know the answer to that question. And I was somewhat surprised that I asked 4 or 5 experts, and they didn't know. But this question reached the ears of Nigel somehow, and he communicated with me with a remarkable speed, as you might imagine, that this conjecture was in fact correct, and he proved it. But this led him to prove, he didn't just answer the conjecture that I'd got, he started a new body of theory, which I'll now mention. We have the notion of a Hermitian operator on a Banach space. If we happen to be acting on a Hilbert space, then a Hermitian operator is going to be, which sits inside a C-star algebra, is going to be just the same as a self-adjoint operator, and we finish up with the theory of C-star algebras. Now, it was well known to people in the Hermitian operator community that it's not true that the collection of Hermitian operators on a Banach space is always the linear span of them doesn't form an algebra. It's not true that the square of a Hermitian operator is a Hermitian operator in general. So we knew there's a very good theory for Hilbert spaces and C-star algebras, and it doesn't work for all Banach spaces. But it apparently escaped the attention of the people who work in this area that if instead of taking a general Banach space you take a Banach lattice, you suddenly do recover the fact. And this is the theorem that Nigel proved, which was quite striking and was, I mean, it's really almost verges on the scandal that not only had nobody answered this question, I think nobody in the operator theory community had perhaps even thought of this question. But Nigel answered this question, and he showed that if you talk about operators on a Banach lattice, then the square of a Hermitian operator is a Hermitian operator. Once you've got that, you can tag into a general theory that involves the Vidaf-Palmer theorem, and you finish up with the so-called fact that the Hermitian operators on a Banach algebra actually form a C-star algebra, which is quite non-obvious. A side consequence of that powerful theorem of Kalton is an answer to the question that I had about orthogonal and band decompositions. But I'd like to point out that Kalton's theorem goes a lot deeper than this. As you might imagine, Nigel wasn't content just to solve the question that I had, and it comes out in this way. Let us take a Banach lattice X now and decompose it as a direct sum of E plus F. I'm going to impose the requirement that the norm of X plus Y is equal to the modulus of X to the P plus mod Y to the P to the 1 over P for all X in E. And it's a decomposition that satisfies that additional property. Well, then Nigel proved that that's already a band decomposition. In this, P is not equal to 2 because the result is certainly not true for P equals 2. But if P is anything other than 2, you get a band decomposition. Now, this is a complex Banach lattice, yes. I haven't got that, yes. I should have said that, and I'm sorry. This is true for complex Banach lattices. It's not true for real Banach lattices. That's a correct observation. And just a little remark about this. Somehow, if you take Nigel's relatively easy proof that answered my question, which involves P equals 1 or things like that, or infinity, then you can run through his proof and see whether it works for P. And it works for certain values of P because there's an inequality that comes into his calculation that's only true for certain values of P, and the lemma that came up in the middle doesn't work for other values of P. But of course you could then ask whether the question is, the general result is true for all values of P. And I think the subsequent pages that Nigel had that proved it for all values of P not equal to 2, rather than for the ones that came up in his easy proof, was a very impressive piece of work. Okay. Well, I'll finish with one other remark about that paper. The story on this, this is if there are people particularly interested in Banach lattices, the story on this is that I was asked to prepare this paper for publication by Gilles, I think, and others. And I have to say I found it quite hard going. It took quite a lot of effort. it became clear that the results were correct, but I had to consult and think and struggle with quite a few cups of coffee to get from one statement of Nigel's to the next one. In the draft paper that was found in the drawer or something, or on the computer of Nigel, there is a final section of that paper that has some sort of continuous analog of the results that I've got. I regret to say that I was completely unable to follow that fifth section, and it's clearly not quite correct as it stands. And then I consulted one or two people in Banach lattices who also attempted this and were not successful in deciphering the fifth section of this paper. It was already a very impressive paper if we delete the last section. So in fact, that's what we did in the published version. The published version does not include the last section. And as I say, in rough terms, this means that there are continuous analogues of the results of Kalton that I've been taking. And if there's anyone here who's particularly interested in Banach lattices and would like access to that fifth section, I can provide that. And good luck if you feel that you can interpret it and find what is probably a good theorem somewhere hidden inside that. But it was beyond me. Well, I see I just wanted to make a little bit of advertisement about some other topics involving. There are many other examples of multinorms that I got a few more slides that I'm not going to get to. So I'd like to advertise that there are a lot of results about what we call PQ multinorms that are nothing to do with P multinorms. And these are tied up intimately with the theory of absolutely summing operators. And the questions that come up in our work can all be translated into questions about absolutely summing operators. And I just want to make one question to see if I can rouse some interest in people here. People who know much more about absolutely summing operators than I do. So I take a number R and I require it to be strictly between 1 and 2. That's because I know the answer for all other values of R. And then I look at n-dimensional LR space. You can see I come from Banach algebras. I put my R at the top, not at the bottom. N is the dimension. And then I look at R prime, the conjugate index, and I take n-dimensional LR prime space. And then I look at a map from the other one that's nothing but the identity map. And then I calculate the norm of that. I calculate the pi QP summing norm of that. Now, this is a number that depends on n. I'm thinking of Q and P and R are fixed. Q is bigger than P is bigger than 1. This is the QP summing norm, and this depends on n. And therefore, it's got an asymptotic behavior that depends on n. I would like to know what the answer is, and I hope someone here will be able to calculate this for me. If you take Q equal to P, the answer's fully known. But if you take Q not equal to P, there are several papers in the literature about this, but I cannot find the answer that I've want. In particular, I'd like to know what the asymptotic behavior of the 2-1 summing norm in this particular context is. And my guess is the answer is n log n to the power 1 over r minus 1 over r prime. But I can't prove that. I can't do that calculation. So quite a lot of the calculations about multinorms that I've got would be answered if I could get the answer to this question. So I'm just hoping someone here who knows a lot about QP summing operators will tell me either that the answer to that question is known or will be willing to have another cup of coffee and work it out for themselves. Thank you very much.